All right, folks, welcome to the last system seminar of spring 2025. Yes, we made it to the end. And we conclude with a special guest, which is Andrea Bastoni, who has traveled all the way from Germany to be here. To be fair, he's here on a stopover because he's gonna head to California in a few days.
Just wanted to add a brief administrative point. You said it was the last system seminar, but there will be a practical security seminar going on in the summer. Systems, but security.
Same slot.
Will it be?
Okay.
What?
Will it be?
I'll put it in the chat.
Oh.
And that one also comes with food, which I know is the most important.
And so no, yeah, it's fine. And then why is a special guest what I consider a special guest? For multiple reasons. I mean, my history with Andrea personally goes back to my first year of university. This is in a weird way, that's the first time we met in Rome. So, we have the same kind of root of origin in this college in Rome. Of course, he left when I was still well underway. And then, in the research community, real-time system has also worked for many companies spanning from, again, he was a visiting student of Jim Anderson, you may know, in the real-time systems community, so UNC. And then he worked for a range of industries in the defense space in Italy. And then Andrea was a pillar of the definition of the PikeOS kernel from Cisco that you may know from literature search, right? That basically does real-time system certified for avionics application, correct me if I'm saying
No, right.
Right? And there's separation kernel technologies and all of that. And then the work was very good and very, groundbreaking, so much so that it wanted to go the next step, right? And the next step is where he's currently at, which is, he's representing two sides right now. One is being Minerva Systems, which is, this startup working in the space of commercializing solutions that are the latest and greatest technology in terms of memory partitioning, resource management at the level of memory hierarchy, again, for application safety critical space. At the same time, he's a researcher at TUM, Germany, where, as I was saying, he wears two hats. One of a postdoc researching, which is also carrying the weight of the role of a CTO for Minerva. Without further ado, all right, I'll leave the stage to Andrea. So please welcome this video.
Thanks. Then it's a great pleasure to be here, actually. So very, very happy to meet all of you and to have the chance to meet some of the people that I've been collaborating only remotely, with for some time. So yeah, as Renato was saying, so I have two hats in this talk. One part is the more research part, and more research oriented, and I will introduce some of the concepts that have been explored and developed concerning basically how to regulate and how to try to make a bit more predictable, basically memory and the memory interconnect on especially embedded boards. And the other part is, so what are the steps that you can do when you try to push more towards industry and towards adoption in industry, some of the techniques that have been developed in research. And so I will switch sometimes all these two hats. And then, so I structured the slide in such a way that when you see both of the logos here, then is both of the aspects being represented. When there is only the owl, then it's mostly just industrial. And so as every good technical talk, I will start with market. So then there is an embedded computing revolution going on, and you have a lot of trends and you have a lot of AI generated things, but not only. So this one, for example, is, so the MemGuard is really, so Volkswagen, what is the name here? I don't remember. So is the Caravelle in German. This one is not exactly but never mind. So this one is one of the prototypes that the people at TUM use and build to have basically autonomous exploration and autonomous driving in general. So there are a lot of trends. So there is this connectivity, autonomy. So you have this software-defined anything you can put after software-defined, basically, Industry 4.0 and so on. But I mean, so these marketing terms, okay, they are backed by some intuition and some technical research, really. So there is a general shift of trying to moving more computation toward the edge. Okay, so towards the devices which are really installed on the car, on top of the car, try to perceive the environment and so on. There are new algorithms, computing intensive things going on. Okay, and for these you normally need high power, high energy consumption, and because the algorithm itself, they are computing intensive. Okay, but on the other hand, so the applications where you want to use these algorithms, okay, they so the application fields where you want to use these algorithms, they are more and more safety critical. So you don't want to use them for your basically computation cluster server only, okay, and shifting sensor just to monitor something, okay, but you want to have something that is related to the life of people. Okay, so you want to use them for autonomous driving, you want to use that for assistant drivers, you want to use them in the field of collaborative robotics, in the field of machines that has to interact maybe with a production line. So maybe it's not the human that is in danger, but maybe it's the whole production line that is in danger, and meaning so money are going to be lost. And you want to have high availability and high assurance systems that are actually using this algorithm. And these systems traditionally, okay, they have not been high power or high energy consumption or server grade. They have been a bit more towards the low power, lower energy consumption for the sake of predictability. Okay, for the sake of being able to have better hooks to analyze these systems. Okay. And so, in a sense, there is this trend of trying to, so this is the real inside of the van that I showed you before. Okay, so basically there is a server rack inside the van, and the van has to be, for example, plugged to the power network before turning on the van, because otherwise you don't have sufficient power only for the battery to power up the system. And so the trend is basically that you are trying to put something that you typically find in a data center setup, if you want. So you want to put container, you want to put Docker, you want to put Kubernetes, you want to kind of do load balancing and so on here, because this is the enabler for what you want to actually deploy. So your complex applications are typically in this way, and you want to put those here, basically. This is the platform that you want to use for this. And this is, for example, so the trunk of a prototype car in Unimore. So it's Unimore is university in Italy, where so via Minerva I'm basically involved with. Okay, so they have of course the universities in Modena, so it's a Maserati car. Why not? The reason is that it was the only one with steering over a wire. Okay, that was available when they started the project. And then basically you want to put very small board there. So, and the enabler for this is basically this magic keyword, which is MPSoCs. So the enabler for this is a heterogeneous board, which are aggregating basically powerful engines. Okay, they are aggregating power, but are aggregating also real-time cores. They are putting on the same board basically accelerators, application class processor, real-time processors, everything in one in order to save power. Yeah, sure.
Why do you need this all local? Why can't you do all the processing offsite?
For example, so in the autonomous driving or so you want to take the decision locally due to latency, for example. So you have so you have a latency, maybe so you have an end-to-end latency in the 150 millisecond order. Okay, and you want to do all your computation part in maybe, let's say, 3/4 to half of these latency span, so that you can also drive the actuators in the rest of the time. And for sort of also cost, I would say, because otherwise you will have, for example, to also certify that the network is capable of giving you the latency under different kind of safety related assurance.
Sure, but humans don't have 100 millisecond latency, right? So we typically project ahead.
They have between the Formula One driver, they have around 100 millisecond, and those 150, something like that. So they are trying to basically simulate these for the two. Human typically have between 300 and 500 milli.
Professional, otherwise it could be like seconds.
If you are distracted, but if you are not, is actually half, basically a second, something like that. This is the typical reaction time that you have. So it's not too far. Yeah. Yeah, sure. And then yeah, I was saying, so basically you try to put the computational power that you saw on a server, okay, on a track, on a server rack, okay, inside one of these platforms. This, for example, so from the technical reference manual of NVIDIA, so this is the Xavier. And so you have the application cores, you have real-time cores, you have GPU, you have different accelerators. And so in order to provide to the end user the performance that they need, okay, but at the same time to balance the power, okay, you want to place a break, of course, from the hardware design point of view. And what you normally do is that you have something that is shared, so that you can more easily transfer data between, for example, accelerators, GPUs, and the cores, back and forth, and so on. And so basically, what you really want to do is that you share the whole memory backbone of the platform. So it's completely shared among all the accelerators, completely, with certain degree of boundaries, okay, but you can consider that most of the time, mostly shared, okay?
Yeah, the GPU is also cache coherent, seems like.
In this one, yes, the GPU has some part of coherency on the video. The NVIDIA is, I mean, this one is not as a beast as this, so they are quite nice. Yeah. This one is actually the Xavier. So the orange is the gray one is even better. Okay. And in order to basically also give to the developer the possibility to kind of control this sharing, okay, you have thousands of what I call it here, so knobs, so configuration tunables that you can actually play with in order to balance the energy consumption, the computational powers, and so on. Yeah. So then we saw that basically these boards are complex, okay, and you want this complexity because you want the performance, okay. But what about the predictability that we are aiming for if we want to move these devices on the edge for safety critical applications? And the traditional safety critical systems, they have been traditionally developed in such a way that they could be explainable in a sense, okay, or relatively easy to certify without too much cost, basically. And they should be suitable for a host of security, safety certification, spanning from the standard industrial, the 61508, automotive, railway, avionics, security, and so on. But the heterogeneous MPSoC, so they have been designed like this by design. And then when you try to kind of do this mapping, is basically going to result in, I would say, integration nightmare. Okay, so it's really putting a lot of burden on the people that have to configure the system to then meet some of the requirements from the certification. So as I said, so the elephant in the MPSoC, if you want to call it like that, is really the memory hierarchy. So the memory hierarchy is shared. So you have a lot of shared components. You have shared connection. You have the interconnect is shared. The caches might be shared between clusters or between different groups of CPU. The interconnect, and then also the main memory, potentially with multiple memory controllers as well. And then you kind of have to try to analyze this. So the latency, of course, with respect to a traditional system that is a single core, single very stripped down in order to enable a kind of reasoning on these. Okay, then the latency when you have sharing increase. Okay, and increase in ways that are not necessarily predictable. Okay, the worst case increase, the average when the worst case increase most likely will also increase. Jitters also increase. So, for example, okay, this is kind of example of what the memory contention could cause. Okay, so sometimes I will just skip basically the description of exactly what it is to give a bit more the feeling about the problem. Okay, so this one is the test is a latency benchmark. Okay, that does memory reads basically from the CPU, and the interference is a stressing memory interference. On this one is on NVIDIA Xavier. And is also using the GPU and the accelerators on progressively using basically all the units that you have available on the Xavier. And as you can see, basically, when the working set size of the interference, so here is the working set size of the interference, here is the benchmark, okay, the time in nanosecond. So when the working set size of the interference increases, goes out basically of what the benchmark is using locally, so the caches, okay, that are locally to, in this case, to the Karman cores, then you start basically all the time that you have starts to increase massively, okay, and you have, so here is more than 10x of basically slowdown that you can have. This is the case of uncontrolled, basically, interference, yeah.
Why do you see the rise before the size of the L2 cache is reached?
This one you mean, or this one?
Yeah, why does it tick up there and not only at the L2 size?
So I don't know. This one is results that is taken from Unimode, actually. So I'm not sure if they have investigated this. We have seen those similar behavior due to the fact that the eviction protocol, okay, you start to evict before, okay, and then you have actually an impact before the maximum size is reached.
But this is
this is
linear or logarithmic?
This seems linear.
So the replacement protocol of the L2 gap is really crappy because this is half the size.
Yeah, that might be.
Significant
Yeah,
impact.
that might be.
Okay.
Yes.
Cool.
Then it probably will be optimized for this case.
But it could also be coherent traffic because you're outside of L1.
But I really don't know how
to
to.
the caches between the CPU and the GPU hopefully are not.
So the internal of the Carmel are not the best, let's say, processor that has been from the openness point of view.
Carmel is similar to a Denver that has DCO, dynamic code optimization.
Something like that.
Gosh.
Yes. And then they switched to standard security. So the Orin has standard 78. Yeah, but this is a good point. So the setup is not trivial. So if you want to understand all of these kind of bits, basically you have to test a lot. Okay, each single setup is different. Okay, and then you have thousands of parameters, and then you need to do this for every single workload. Okay, and of course you change the board, and then you need to have something. You need to repeat the kind of test.
Is this for a single workload, Professor?
Sorry.
Was this for a single workload?
You mean the benchmark or the workload, the Trex and G?
Yeah, the benchmark itself.
The benchmark itself was a single workload. Yeah. So, is predictability possible at all? Okay, on these SOCs. Okay, and actually coming from the willingness in ensuring actually more quality of service in the server spectrum. So for data center, okay. So providers of chip, okay. So Intel, ARM, and so on. So they have been working at techniques that you can also use in order to improve the overall predictability. So trying to basically mitigate the interference that you actually have. So, and then for example, so these are the techniques that can be perhaps misused, okay, because they are not really designed for initially for the purpose of being used for doing real-time or kind of predictability in the sense of safety, okay, but more for quality of service, because otherwise on data center is a mess. Okay, then these techniques from both the hardware point of view and the software point of view can be broadly divided into caches, targeting the caches, so having possibility to partition caches to a certain degree. So, and if you have hardware, then it makes sense to partition that per way. I will get a bit more in details into this. Okay, and then the interconnect. So how to regulate the interconnect between the various day master that are talking on the interconnect. How can you try to regulate something? Okay. The technologies, some of these are relatively new. Okay, relatively, okay, on the Intel side a bit more dated, okay, but they are not necessarily working for the kind of setup that we want. For example, so Renato, so and the
author is right here, so.
Yeah, okay.
I was just asking.
Okay. There have been work analyzing these. I will come a bit more. I have taken some of the results of the paper in early perspective. Okay. And so, this one is the work that one of the students, my students in the group, will present next week at Artas. Okay, so this is the kind of equivalent for the cache partitioning only. Okay, on ARM. So, and I just listed some of the technologies. So on ARM, you have the dynamic queue shared unit, so DSU, or MPAM. So it's a longer name, so it's whatever is MPAM for everybody. Okay, Intel has this resource director technology divided in cache allocation and so memory bandwidth allocation. And AMD has equivalent, basically the same as Intel, but they call it quality of service. Okay, and the API between Intel and AMD is pretty much very competitive. On the software side, you kind of have the same. So people trying to emulate what you have on the, I mean, not emulate, it's the go-to point, right? So this is where the interference lies, and then you try to mitigate this type of interference. And then same here, so from the caches, but using then set partitioning instead of way partitioning, for the simple reason that you can implement it better in software, leveraging the NMU, basically. And then on the interconnect, you have memory bandwidth regulation. And these techniques, especially memory bandwidth regulation, so if you want, is pretty old, okay? Because, so I don't know if you know Mancuso, okay? And then the technique is quite an old study. It's from 2015. Yeah, exactly. Yeah, this one is basically cache partitioning, okay? This one is, so Renato is always involved also here, and this was for bandwidth, okay, regulation, and then a bunch of other papers. So, and this one tries to combine all of the aspects in a more coherent way, unified way. So this is one from TUM, and this one is also from TUM, and this one is collaborative work between TUM and BU. So as you can see, the actors in this field are a lot. You have TUM, you have BU, you have BU. No, I'm kidding. But sometimes there is also Barcelona Supercomputing Center, okay, and there is Kansas University. So I'm kidding. But some of the interesting results and the one that of course I'm presenting, so are coming from our. So the advantage of software techniques normally is the flexibility there to hardware. So, and the possibility to apply more or less the same techniques across a larger spectrum of work. Just a brief recap basically about cache partitioning. So I was mentioning cache partitioning in software. You normally want to do it like set partition. So basically you want to color the set and you want to control basically where is the allocation of you can do it by per task. Normally you do it at core level. So you control basically, you control the exceeding bits out of the page offset in order to control the mapping and then select which set one core is forced to use. Okay, and on way partitioning, you need hardware support, and normally you have something that is slightly more flexible than just core pinning. So you have like actors or cores in this case, so masters normally, which are assigned to an ID, and then the ID defines the way partitioning, and then in this way you define the mapping. But basically, this is the techniques are more or less always the same. It doesn't matter if you are on Intel or if you are on. Okay. You want to have, of course, in order to use them properly, you want to have some operating system hypervisor support here, especially for cache coloring, okay, because in a sense, so this is the other name of set partitioning, so coloring, because you are coloring part of the cache by playing with a bit, okay, and especially for coloring, so if you want to implement this in software, it makes normally a lot of sense to implement that at the hypervisor level, because in this way, you can play with the IPA to PA translation, okay, and so the operating system is completely unaware of the fact that this color. Okay, and so this is something that is a nice basically way of implementing it. Okay, so that you actually keep the operating system completely unaware of this. And this is, for example, so what we have being implemented in JLAWS hypervisor. Okay, so the code is available. We have multiple supported platforms, mostly ARM, but on ARM we have quite a lot of platform support. Okay, and this is a shared effort so between Minerva, QM, Boston University, and that spent for quite a long time. So because, for example, so this is one of our employee actually, and this is the master thesis in 2019, and so it doesn't matter too much what is presented here. So regarding the setup, this is a setup with Ethernet and the various scenario. So the important part here is that the bare metal benchmark, and this is in this case was the frequency and the response time. So the higher the response time, so this is just a spectrum plot. So the frequency, here is the occurrency, okay, and the response time, the higher the response time, the worse for the network. Okay, and so this red curve is the one of the bare metal, basically without any type of interference on JLAWS. Okay, then in the moment when you add the hypervisor, okay, you have a bit of overhead, but as you can see, it's not too much. Okay, but in the moment when you add the interference, then your curve will basically shift, and you have quite considerable basically shift into the response time. When you add coloring, which in this case works, okay, then you basically get this curve here, this lila whatever, okay, and basically get results which are comparable to the one with the hypervisor. Okay, and I said when cache coloring works, it is because so cache coloring is obviously. Well, I mean, you're removing caches from your workload. Okay, you're removing usable caches from the workload. So you need to check whether this is exactly what you want to have, because maybe it's not the right solution for you. In this case, it is clearly. Way versus set partitioning. Which one works better? This is spoiler alert. This is something that the student will present next week. Okay, so attend the presentation from whoever is coming to ARCAS. Okay, this is on newer platform, newer ARM platform. So this is two Rockchip. So, but they both have so ARMv8 and so on. They have relatively new cores, so 55 and 76, and they have these DSU, this dynamic view. And the benchmarks here are San Diego Visual Benchmark. The important part here is that independently on how you partition, so in this case it's set partitioning, in this way is way partitioning. Okay, this column is way partitioning. So this is, so the blue bar is what happens when you don't color, okay. The other bars is what happens if you color. And as you can see, okay, then pretty much they kind of reduce the huge difference that is the huge slowdown that you might experience when. And if you're asking why is these spikes so decreasing, okay, this is something that has to do basically, this is an artifact, so it's explained in more details in the paper. This is an artifact on how you have to deal with the interference, okay, which is actually, so when you're here and you have no cache partitioning, okay, then basically, so the from here to there, once you go at the boundary of the L3, and you surpass the boundary of the L3, it is the interfering workload that is taking more time because it has to also access memory. Okay, and the fact that the workload is lower, okay, makes the benchmark faster, but it's actually the interfering workload that is going slower, freeing up L3 for the benchmark, and the benchmark gets, it took a bit to figure that out and be sure that that was the.
But that also means that your L3 has enough MSHR to accommodate for those
Yes.
pending transactions while still serving hits from the benchmark. Okay, interesting.
Yes. And of course, this is for the pen. So for example, on the ORI, it doesn't work. Okay, so, and it doesn't work anymore. Our suspicion there is that, of course, you have another level of cache, as you can see, and this one doesn't play along well with the coloring. So, I mean, it is more complicated. So the L4 on the ORing doesn't belong to the same kind of pair-way partitioning. And then it is poorly documented. So we have kind of to guess what is the size of a cache line there. Okay, and then, so, I mean, for way, in this case, it was way partitioning, but it doesn't matter. Also, set partitioning doesn't work that way. And yeah.
Quick question, just at what you said, we had to guess at the size of the cache line. Don't the people who do cache side channel do this for a living?
Yes.
Okay,
Yeah.
they couldn't help you?
They
Tell you, run this, and it will tell you what the size of the cache line is?
Yes, but at the moment we haven't tried that. Okay, yes, but this is something to look into, but we haven't tried that. Yeah. And the thing was observed basically. This is from the RTNS paper. Okay, and so for example on the Ice Lake, the cache allocation work, and on the Cascade Lake it doesn't work too well because at a certain point then results start to basically the slowdown increases. Okay, and so the quality that you can get is really, so it's not necessarily given. So you have to test it and you have to try to get familiar with the board that you have at hand. So on the hardware side, so you have all these tunables and so on. And so the paper, this RTNS paper, shows in more detail that also from the memory interference point of view. Okay, sometimes it works, sometimes it's not. Generally speaking, it works a bit better than the cache allocation, but not necessarily. Okay, at the moment, I'm not aware of any study that tries to do this with AMD. Okay, so the quality of service of AMD is a bit of a black box at the moment because we have to take a look at that. And MPAM is interesting, is promising in the sense that MPAM compared to the quality of service of Intel and so on. So they have a more fragmented environment from the hardware point of view. So they integrate normally pieces from more, I would say, suppliers than what Intel or AMD have done in the past. Okay, and so they have came up with a specification which specify different knobs and kind of tunables that you can specify at different level if you want to be compliant with this kind of specification. Okay, the fact is that the specification, so I'm aware that there are non-public and not available under non-NDA so implementation of MPAM that has been there for quite a while, because MPAM is a ARM v8.2 plus specification, so quite old. Okay, a bit more available from the .4. Okay, and so the only platform that has something that is available, okay, is this Ratza Orion, which is basically already sold out, and we are waiting for the next batch. We were able to buy only one, and we are not sure whether MPAM is actually. I mean, it says that MPAM is there, okay, and we don't know if you can configure it. We haven't. So the platform is basically one stable release every couple of days. Okay, so from the point of view of firmware and so on. Yep. And at the moment, there are no practical studies available for MPAM. So
What's the manufacturer? Rat?
this is a Chinese thingy. Okay, so it's the same of the OC5B, I think. So it's a
Hard channel.
so and these are RV9. So from the software point of view, okay, these techniques, these MemGuard techniques from 2013 is a quite established techniques from going from the hardware to the software point of view for bandwidth regulation in software. These techniques is quite old. Okay, and the basic idea of the technique is I use performance counters, which are normally widely available, especially on these boards, because they have a lot of knobs, a lot of configurables, and they have a lot of performance counters that you can normally access also. And then I'm basically monitoring what is the interference perceived at the interconnect level, normally in a proxy way. So you take a look at the caches, normally at the last level caches, and you try to basically understand from the values that you see in the performance counters at the last level cache, okay, what is the workload that the various cores are posing on the interconnect. You monitor these. When these exceed a certain threshold that you can configure, okay, then you want to program this performance counter to trigger an interrupt so that you know that something bad has happened. And then in that moment, you want to either schedule or stop the core or schedule something that does not access memory and so on. And of course, after a while, you want to restore the previous situation. So you have a periodic way of replenishing the budget that you have set, and then a way to basically get informed in case that something went wrong. And of course, you can get quite high overheads. I will get into these basically later. Okay, but basically means that you get two interrupts. So you get an interrupt for the replenishment, and you get potentially an interrupt in case that the the accesses has exceeded the threshold that you have set. So something that is low granular is not really possible using these mechanisms. Okay, but of course the mechanism works. And it has been implemented in multiple versions, so it's been implemented at operating system level, has been implemented also for Intel. It works also on Intel, not with these kind of JLAWs, does not, not in JLAWs, but on, so the implementation from each tool, for example, is always Intel. Okay, code is available, and then as you can see, you configure basically the interrupt of the interrupt that you want to receive for your performance monitoring unit, and then you can set up basically the various, you can enable, disable, and you can set up the period, the budget, and the type of event that you want to use and want. Okay, and it works. Okay, so same, this is an evaluation in the context of the Hercules project, which is the one that was deploying this into the car. Okay, so it was deploying some of these techniques into the car. Okay, and so here is the same. So this the interference. So is the baseline time relative to baseline for different type of basically kind of a benchmark that we are monitored here. And in this case, if you have interference and if you have the reference is without the MemGuard protection, and then if you have the MemGuard protection, then you are basically almost achieving the same performance as without the interference. Of course, you have to configure your system correctly, in a sense, and you also have to take care about the system configuration. Because, as I was saying, so you have two interrupts, okay? And especially the regulation period is quite bad, because so the faster you want to regulate memory, because you want to be more precise in what you enforce, so that the other cores are not so penalized that much, then the more is the slowdown that you pay. Okay, and so you can pay quite a lot. So it's 2.4x slowdown is quite considerable. Yeah, not x, sorry, 2.4. So slowdown is considerable. And typically, then you end up with something that is in this range between 600 and so 1,000 microseconds. Typically, you set 1 millisecond resolution, and you have these large blocks of basically regulated kind of memory access. So Something that we studied recently, so it was from 2023 to 2024, started before that, is normally these platforms, so this heterogeneous platform has multiple cores. So what about if we use some of these cores in order to take a look, okay, at what happens to the other cores? Can we use this fact that we have multiple units available? So similarly to what part of Renato research is doing by using the FPGA to try to take a look at something that is happening on the platform, can we also maybe use the standard, so real-time cores that are available on these platforms to program something that is giving us, instead of giving interrupts, is giving something different, okay? And so the answer is yes, okay? And so with this technique that we call mempol, okay, because it's policing, but at the same time it's also polling, okay, the information, instead of basically programming the PMUs to trigger an interrupt when a certain threshold is reached, then you have a polling mechanism that is monitoring the performance counters from, in a sense, the outside of the monitor core, okay, and gives you the possibility to do both monitoring and regulation of the memory bandwidth by having basically polling of the performance counters. In details, the techniques takes a look at the performance monitor unit registers, okay, because they are mapped. It accesses those using core site infrastructure, so debugging infrastructures, okay, and then uses a technique which is very similar to a hardware debugger to do on and off of the cores. So a debugger can basically stop a core and then let it run again. And the registers to do this from the debugging side are also available and exposed. So we misuse those to basically do this with the regulation. Yeah.
I was pointing.
Quick question, when you say the machine-specific registers, the performance counters are mapped into memory so that the R core can read them. How are they synchronized? I suppose they're not updated at the frequency of an event that they're monitoring, because these events can be.
Correct. In fact, you pay a bit of a latency. So this is the latency that you pay to access those. Okay.
Sure,
so
but that's just.
No. This is the end.
I see. So it's not in.
Yeah.
Okay.
And then basically, yeah. And in fact, the polling cycle, okay, then basically need to take this into account. The polling cycle needs to be fine-tuned for the board, okay, because otherwise then you read the wrong values. Yeah. Implementation and applicability, it turns out that, so for example, so this one on the ZCU, you can regulate it like 6.25 microseconds, but on other boards, like for example, the MX8 or so, you need longer, so it's 10. And then on TI, but it turns out, so the take-home message here is that this technique, even this technique, is also applicable to a very large spectrum of ARM boards. Okay, so a lot of these boards, they have combination of, so if it is not an R core, it is an M core, it is an M4, an M7, doesn't matter too much. You can still, so unless it is an M0 where you have no space, okay, but yeah, I mean, so you can implement it. And one of the things that for both MemGuard and mempol, and in generally speaking, all these quality of service techniques you have to take into account is, so which bandwidth do you set? Okay, so what is a good bandwidth that you should set? Okay, and this concept of the good bandwidth that is supposed to be set on the platform, okay, so what is a safe one, what is a good one? This concept was also not really explored, okay? So basically, so there was some work from Renato and some work from us trying to kind of infer or try to explore a bit or go into the direction of defining a bit more formally what is the safest bandwidth that you should enforce. Okay, and we formalized a bit this concept into what we called the sustainable memory bandwidth. Okay, and we also defined a procedure which is an empirical approach to try to figure that out. Okay, that works quite well also on newer boards. So we tested also that on DSU-based boards, on ARM, works quite nicely. And yeah.
Isn't the bandwidth inherently dictated by your real-time workload?
The worst case one, yes. So the worst case one, in fact, so here, this is basically some of the plots that we get. So depending on the board, okay, the worst case bandwidth is typically the one that will cause a row miss into the memory controller each time that you basically do a request. Okay. The details of the configuration and the layout of the memory controller and of the DRAM, okay, are not necessarily available, okay, and so in previous studies, for example, in this one, okay, so 2021, okay, we were the details are available, and so, for example, our workload was exactly hitting the right column and the right row in order to basically getting the worst case bandwidth that we could be able to extract. And we developed something similar to, is similar to a pointer chasing, okay, which is accessing with progressive offset. And we found out that it works quite nicely and we are able to get the safest and lowest. Not necessarily the best, okay, and not necessarily really representative of the workload. So not all of your core are doing at the same time exactly these. But if you want to be safe, then this is something that this is a parameter that you have to find out.
You're telling me that DRAM manufacturer, when they sell me the peak bandwidth, they lie?
They don't. I mean, they really they don't.
ISP?
Exactly.
For example, so on the all-in, okay, only from the core point of view, we are not able to extract the maximum bandwidth. So you don't get the safe. So just a quick high view, basically view difference of so MemGuard and MemPol, how do they work differently? So you have this one, basically the course regulation of MemGuard is like this green part. So for half a millisecond, okay, you stay on. Okay, for half a millisecond you stay off. The average is here. Okay, for MemPol instead you pol all the time. So all these bars here are basically the MemPol, the on off. Okay, and then you get basically the same type of average in the end. Okay, but the average, of course, you can average on a lot finer granularity. MemPol also allow you to do more than MemGuard because so MemGuard is bound to the interrupt, if you remember. So you can implement a sort of just max or min function because the first interrupt that hits, you have to react to that. Okay, with MemPol, since you're polling, then you can have a function of different behavior of the performance counters. And then in this case, you can, for example, regulate also read, modify, write, or you can react to things where MemGuard cannot. So MemGuard regulates on these, so L2 refill, and then it's basically only considering the reads. And so it's not able to see the write backs. Okay, and then if you consider the reads plus the write backs, then of course you can react to both. Okay, and then so this is, for example, one of the possibility of MemPol. Okay, and you could redistribute the bandwidth, right? So you can have a global controller and a local controller. So the local controller is controlling what the cores are doing, and the global one can kind of monitor the overall availability of bandwidth, and then decide, for example, that if this core is not using the bandwidth anymore, so maybe the other core could use it. Yeah. Of course, also MemPol has limitation, and in particular, so some of the limitation is that the core sites might not be available. So it's a debugging interface, for example. So when you want to do regulation, maybe this is not given. So the regulation is using a debugging interface, is not ECC protected, blah, 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 and then maybe you cannot use it in a certification. The view memory registers needs to be available to the other basically side. So this also might not be given. And then the notion of sustainable bandwidth, I mean, so this is something for both MemGuard and MemPol, of course, but it's something that maybe you can do more than the safe, yeah, and it's still safe. So, but back to the original objectives of, let's say, the presentation. Okay, so we want to control memory interference on MPSoC. Okay, and we want something that is good enough to support maybe safety and security certifications because they focus on the analysis of the resources in isolation. They focus on the absence of interference channel, this freedom from interference between the different partitions that you wanted to set up on the system. You wanted to focus on the worst case scenarios, so the predictable performance and so on. And also some of the tests that you do, you want to aim for the worst case. Just aiming for the average case doesn't bring too much, okay? Because it's not given that if you improve the average, the worst case will also improve. Okay, the other way around might be true, but generally speaking, no. But on MPSoC, as I was saying, so the resources are shared by design. So this is intrinsically complicated, and I hope that I've given the feeling now that there are techniques that we can use, okay, but even the use of these techniques is complicated, and the use of these techniques is complicated because these boards are complex, and we have a lot of tunables and a lot of knobs that we can control, and each time we have to basically replicate everything on the board. Okay, so how is basically a developer, okay, supposed to just find the right configuration, right? So I need just to find the perfect configuration for my board, and I want to use some of the hardware and software techniques, and still, okay, how can I choose which setup? How can I choose also the workload? Because depending on the workload, you might get this safe boundary, or you might get something that is not safe, but maybe good enough. Okay, you can control maybe way partition is working for you, maybe set partitioning is working for you in that case, and so on. So normally, what the developers would like to have in this case is a tool. Okay, so I want to have a tool, and there are plenty of tools out there. Okay, and this is where then we saw basically the opportunity to kind of transform some of these techniques that you have seen from the research point of view, where there is a lot on investment on trying to analyze the behavior of the board, into something that somebody that does not have the skill, okay, of a PhD student could try to use in a sense out of the box, okay, and get some results that can then be used to support certification activities. Okay, and this is the part where you go basically towards the kind of industrial, let's say, part, what we do in Minerva. Okay, and so we have developed a way that is partially based on mempo, okay, but it's a bit more. So you basically present a way to understand, so the kind of memory causes of time interference. So have a way to aid the developer to see, wait, sorry, I have to go here. So to see basically your task in execution and see the memory associated to the task in execution, okay? You have a way to basically see what is the, some statistics related to the task. So the CPU utilization, you have a way to search, you have a way to kind of inspect, you have a way to measure time, detect periodicity for some tasks in an automatic way, some of the things that you typically want to do, okay, but at the same time also be able to generate stress in memory, different type of stress, okay, and then analyze, for example, what is the behavior when you activate this type of stress, and what is the behavior also on the rest of the platform, and you get a very kind of responsive feedback about what is happening in the platform. So the whole GUI and so on works at something like 60 FPS. Okay, so you get a very responsive kind of view about what is happening into the platform, including and on top of the ability to record. Okay, so when you do normal debugging session, you could do this with a Lauterbach, okay, but you get basically for, so I don't know, this one is already 35 seconds of execution traces. Okay, I mean, this one allows you to trace for hours. Okay, and a Lauterbach, I mean, of course, a Lauterbach trace is a lot more, but then you get a lot more data process. And you also want to be able to then select the knobs that you have identified using the tools, okay, and then put them back into an updated setup that you can run overnight, for example, and integrate these into so a sort of CI/CD kind of basically way of doing your regression testing. So, and we have developed basically a way so that you can put in the same kind of knobs, okay, that you have stimulated using the graphical interface into then your TIC. The hardware support, yeah, Xilinx and XP, different operating system, because of course one part of the support is operating system dependent. and yeah, so spectrum of the support that is useful for developers. And of course, so if you consider the whole system, then in this part is where mempool, for example, in this case we use mempool, okay, a mempool-like monitoring and regulation. This is the part where it comes into play. Okay, the rest is what you have to basically develop on top in order to enable developers to use it proficiently. And it works, actually. So we have been used, for example, so this is an example of a benchmark, okay, that has, say, some different execution times depending on the different type of interference. So we had a problem that a customer was not able to understand what was the main cause of one of the slowdown that we are seeing. Okay, and then we simulated basically their application using a benchmark, and then we used the architecture to quickly, okay, because so this part is really so less than 13 minutes of tracing, okay, to basically stress the system into different configuration, okay, and then try to basically understand what is the CPU utilization, how that was changing, and then as you can see, there is sensitivity to L2 thrashing, okay, and there is sensitivity to linear writing. Okay, but for example, so worst case writing pattern are not affecting the benchmark too much. Flush clean mapping operations as well, not too much. Okay, and prefetching a bit more. And then you can do a kind of parametrical. So using this API, as I was mentioning, you can do kind of parametrical investigation of the system. And for example, so you can increase the memory bandwidth that you give to the various cores, okay, to try to find a situation where, for example, so if you give 1.1, 1.2 gigabyte, okay, then the system behaves quite stably, it seems, okay, but then when you increase that too much, then the system will basically cause some deadline miss. And then you can study also what is the kind of sensitivity. So that one was memory bandwidth. This one is what is the sensitivity when you do the regulation, but you change the type of workload. So the previous one was writing, okay, and this one is so L2 cache thrashing, okay. And then you can see that, for example, so the CPU utilization decreases in groups, okay, but the spikes are still there. So for example, here maybe a cache partitioning technique may help, okay, and this is something, the kind of trade-off that the tools allow an unexperienced developer, okay, unexperienced in the sense, experienced in his domain, but unexperienced of the board. And so in conclusion, I hope that I kind of convinced you, okay, that the complexity of the MPSoC is actually needed, okay, but this drives against the kind of safety features or safety activity that you normally want to perform on these boards and workload if you have the need to use newer type of performance intensive applications into the edge or safety critical domain. And there are techniques that you can use to try to balance basically performance, safety, and so the amount of interference, but they are complex and very time-consuming to configure correctly and to understand correctly. And then towards the end of the presentation, basically, I show you some of the possibility that, and also the kind of effort that you have if you want to make the techniques from the academia to be usable in the industry spectrum. And that would be, the last point here, this is important. Note that I also talk about CPUs, okay, and how to regulate the CPU. I/O is not there. So I/O is following a completely different path and normally completely unrelated, is non-coherent. You have different ways of reaching memory. Is something that requires, is still quite an open, not necessarily open, but is still a research question. Some of the hardware techniques that I presented apply to I/O when they are correctly implemented. Yeah, and then go back. So, okay, thank you. That would be it.
We have reached the top of the hour. Actually, went a little bit over, but we have the room, right, for a few more minutes. So maybe we can take a couple of quick questions from audience before we wrap up.
One of your slides, you say you find out what is the safe sustained bandwidth that you need for an application. But I'm assuming most of the applications you're observing are just not dealing with real world actuations to the outside. So like, are you just measuring how long does this application reach a deadline in terms of compute or in terms of actuation?
For the sustainable bandwidth, you mean?
Yeah, the safe sustainable bandwidth. that you need.
Yeah, I mean, the safe sustainable bandwidth is, so how do you determine the safe sustainable bandwidth is something that is memory controller and DRAM specific. It's not necessarily application specific. So you use a benchmark application to determine what is the safe kind of, so there is an interesting, so the best probably visualization of the effect that you have into memory is in one of your papers, in the e-work paper. So basically you see that the, so when you are below the sustainable bandwidth point, the contribution of each single core, okay, is additive. Okay, if you are above the sustainable point, okay, then God knows. Okay, and this is what is basically there. This is kind of unrelated from the point of view of the latency that the applications will perceive, okay, in the real world, because that depends on how much bandwidth you let them have, okay, which type of regulation they are under. Okay, so it's mempool or MemGuard, for example, and then also the application itself. Yeah?
Just to add to that question, are now basically is the default assuming that all memory controllers are going to come with like counters that let you exactly measure these things, or is there like something, because like clearly MemGuard is not using that, and that like you know it tries to do PMUs. So is there an alternate that we can do rather than just relying on these specific hardware counters?
I mean, not really, and this is something that is really board specific. So if you, so the S32V, okay, had the counters also in the memory controller, and there is a paper from I think
The Bosch Fox.
the Bosch Fox. No, there is yes, they. And also, I think the people in Pisa also use that. Yeah, to kind of basically understand directly from the memory controller what's going on. Okay, this would be kind of ideal because then you also get what is the I/O doing. Okay, for example, and instead with these techniques you only get the I/O in an indirect way by monitoring what you don't get, which is not particularly precise. But I don't know. So maybe with PAM, okay, people will make this information more available. Okay, but it depends whether the memory provider people will actually implement then the MPAM standard.
Because like Intel also talks about their like exact like cache occupancy and like the counters which like don't work as necessary, and they're not.
Yeah.
They have so many more memory controllers.
But they are also in a much worse situation, I would say, than ARM, because I mean, I don't know, not much worse, but so they have been dealing with complex CPUs and complex cache architecture for a lot more time than ARM. So I mean, only the starting from the Neoverse, then you get something that is decent from the performance point of view. Okay, but otherwise, so I mean, ARM normally has a more straightforward design than the Intel one. So yeah, Intel, but also NVIDIA and so on. So they already have quite a lot of framework, which gives you also access to the performance counter, all the different types of performance counters. Whether then you can use for something different than monitoring, or whether then some of these are also accessible from the vantage point of view that you want to use. So if you want, for example, with mempool, okay, then you need access to the performance counters from the R core. Yeah, but maybe this is not given. So, for example, we were never able to implement mempool on the Xavier, okay, because the firmware was always playing against us, okay. On Biorin, we know that we see all the core side, for example, but we would need to flash the firmware in a non-supported way, which could basically break everything. So yeah, and so on. Yeah. So all these kind of things are there, are not in the presentation, but you know the complexity of dealing with this stuff.
Now, one thing more about memory bandwidth, right? So, I mean, we discussed about how like the hardware support that we have is shaky. And there's a lot of people that still rely on either you do something like MemGuard or your best bet is something like MemGuard, so a software-based solutions. Is it really no other tools than just these two in your experience? Did you find something else or just that?
I would say, so in my experience, it's just that, okay? Because for most of the cases, it doesn't matter. Okay, so far, okay, it has not mattered. So the kind of shift, so I started at the beginning saying that there is this shift towards more safety on the edge, okay? And so before people realize that maybe they need something better there, okay, it takes quite a while. Okay, before this moment, at the moment you only had the problem into, if you think about the quality of service and so on, those are for servers, data centers. They have the problem that they want to build some virtual machine users more or differently than others. This is why they have that there, okay, while still multiplexing. And this use case is clear, and this use case is also kind of easy in the sense that you only provide service level agreement. Okay, so if you, and then a certain amount of time that you kind of enforce yourself to, but I mean, 99.9%, okay, is nowhere near to the 99.69 or 59, okay, yeah, and so then it doesn't matter too much, okay, and the real situations where memory bandwidth regulation or this kind of basically fine-tuning of the caches really matters, okay, is for selected use cases where you have people really trying to push the maximum out of the embedded board, okay, while at the same time having maybe a Linux on a couple of core, real-time loops on the other, controlling an FPGA or controlling really so actuators that needs to respond in a couple of milliseconds. Yeah? So it's limited, but is getting towards the direction where this kind of application is not limited. And so, for example, so I think that is AMD, so Stefano Stabellini from the Zen community, okay, that is also with AMD, has been now, I think would be probably the 10th iteration of the slides that I've seen, more or less always the same. And he's showing, so basically one single hypervisor spanning on an x86 machine, and the other part is an ARM machine, controlling at the same time, so infotainment on the x86 side, and then the real-time advanced driving support on the other side. Okay, so there is clearly a push into this direction, and now there is also more of a kind of critical mass that is going there. Yeah.
I mean,
And we can take the last question.
Yeah. Like the research groups that exist like in the real-time communities, they can keep publishing papers on how to either use or abuse these debug infrastructures or, you know, these registers. But I mean, Minerva as like a company in the industry, do you find that your voice is more heard than regular researchers that are in a conference that say, oh, this is a good idea, but you're actually making a tool? Do you have more communications with manufacturers with
Oh, yes, I do.
Okay, do they actually listen to you though?
They listen to you only to the degree of amount of your customer critical mass that you have. Okay. Some of the manufacturer, they listen to us, but they also listen to the research community. Okay. But so, I mean, if you have like, if you have helped big customer names,
They will.
okay, then they also see the economic advantage of, say, listening to you because they see the opportunity to sell more of their boards. Okay, and in the research, everything is just research, and then they cannot go. I mean, they go to the director, okay, but then there will be the next research project coming out, not necessarily something that will translate into real support on the board. Yeah.
We have 3 riders by definition.
All right, well, thank you for